Welcome to this educational video where we'll explore a fascinating discovery in quantum physics, the hidden quantum geometry or quantum metric that affects electron behavior in quantum materials. This discovery, made by researchers at the University of Geneva, reveals how electron paths can be warped in specific materials, similar to how gravity bends light. Let's break down this complex concept into understandable parts. First, let's understand what we mean by quantum metric. In classical physics, we're used to thinking about geometry in terms of distances and angles in our familiar three-dimensional space. But in quantum physics, particles like electrons exist in a more abstract mathematical space called Hilbert space. The quantum metric describes a special geometric property of this space, essentially how curved or warped it is. This warping affects how electrons move, similar to how the curvature of space-time in general relativity affects the path of light around massive objects. The University of Geneva researchers observed this quantum metric at the interface between two materials, strontium titanate and lanthanum aluminate. When these materials meet, they create a special two-dimensional environment for electrons. Let's visualize this interface. At this boundary, electrons can move freely in two dimensions, like cars on a flat surface. But the quantum metric creates invisible hills and valleys that affect how electrons move. What makes this interface special is that when electrons flow through it, their spin becomes linked to their momentum, a property called spin-momentum locking. This creates a unique quantum geometry that affects electron transport. To understand this phenomenon more deeply, researchers have developed a mathematical framework called the Inverse Master Unified Frequency Equation, or IMUF. This equation describes how forces between charges depend on frequency. The equation looks like this. F of omega equals lambda times q1 times q2 divided by omega squared times r squared, multiplied by a threshold function f. In this equation, q1 and q2 represent charges, omega is the frequency of interaction, r is the distance between charges, lambda contains fundamental coupling constants, and f is a threshold function that determines when the interaction becomes significant for the quantum metric. We can apply this equation to electrons in the interface. Here, the charges are electron charges, the frequency is in the terahertz range, and the distance is at the nanometer scale. This discovery of the quantum metric has profound implications for various fields. In electronics, understanding how electrons move through quantum materials could lead to faster and more efficient devices. The quantum metric affects electron transport, which is fundamental to all electronic devices. For superconductivity research, the quantum metric could help explain how electrons pair up to flow without resistance. This could lead to room temperature superconductors, a holy grail of materials science. Perhaps most exciting is the potential for ultra-fast devices operating at terahertz frequencies, that's trillions of cycles per second. These frequencies lie between electronics and photonics, offering new possibilities for communications and sensing technologies. Let's visualize how the quantum metric affects electron flow. In a normal material without the quantum metric effect, electrons follow relatively straight paths, experiencing only regular resistance from the material. But in materials with a strong quantum metric, electrons follow curved paths due to the warping of their quantum space. This creates additional resistance in certain directions, particularly when electrons try to move upstream against this quantum geometry. Researchers observed this effect by applying intense magnetic fields to the material interface. The magnetic field enhances the quantum metric effect, making it easier to measure the changes in resistance. Let's look at some calculations to understand the magnitude of these effects. Using the IMUF equation we saw earlier, we can calculate the force on electrons in the quantum metric system. Plugging in the values, Lambda EM is about 1.02 times 10 to the 21st. The electron charge is 1.6 times 10 to the minus 19th coulombs. The frequency is about 10 to the 12th radians per second. The distance between electrons is about 1 nanometer or 10 to the minus 9th meters. This gives us a force of approximately 2.6 times 10 to the minus 17th newtons. While this seems tiny, it produces an electric field of about 160 volts per meter, which is strong enough to create measurable changes in the material's conductivity. To summarize what we've learned about the quantum metric: 1. The quantum metric is a hidden geometry that warps electron paths in quantum materials. 2. It was observed at the interface between strontium titanate and lanthanum aluminate. 3. It creates effects similar to how gravity bends light in space. 4. It can be described mathematically using the IMEO framework. The discovery of the quantum metric opens new possibilities for understanding and controlling electron behavior in materials. This could lead to breakthroughs in electronics, superconductivity, and terahertz technologies. By revealing how quantum geometry affects electron movement, scientists are gaining deeper insights into the fundamental nature of quantum materials and how we might harness their unique properties for future technologies.